So I'm not sure because it's not clear to me if it is too advanced or too obvious, but since you can ask questions, probably through our interaction, we can kind of correct and adjust what I'm going to say here. So we should be talking about dark matter today. This is what I was assigned for. But before talking about dark matter, maybe it's better if we do some introduction about matter. So the title I had to discuss today is this one. But I will start from the opposite one, which is the bright side. The bright side, in a way, is what we see, what we observe, what we know about. And this is a list of the names of the particles that are pretty well known in particle physics. The first one is the electron. Everyone knows about the electron here. Then there is the muon, which is a kind of partner of the electron. It's heavier than the electron. It's about 100 times heavier than the electron. And there is the tau. And then there are the neutrinos. Probably you heard about neutrinos in the last few, well, in the previous lecture. And then there are quarks, the U quark, the D quark, and the S quark. As you can see, we repeated them with different colors. Indeed, in the case of quarks, there is a new kind of charge, which is called, it's a different kind of charge, not new. New is not the right word for it. It's a different kind of charge, which is called color. You know that the electrons come with a charge, which is a minus charge. The proton comes with a plus charge. And I didn't put the proton in this list because the proton is a composite particle. These are elementary particles, like point-like particles, the real building blocks of matter. And so they have electric charge. They have an electric charge. These quarks have an electric charge, which is a fractional charge. But they also have another kind of charge, which is color. And this is why I draw them with different colors, red, and this should be a blue, and this is a green. So this is about particles with mass. All of them have mass. Then there are a couple of particles which have no mass, which are the photons and gluons. The photons are everywhere. You know very well about them. And gluons are kind of colored particles, also them. And they are responsible, as we will see in a second, of the fact that quarks are together in protons and neutrons. And then there are other two kinds of particles which are well known, which is W and the Z particles. So this is a list, just a list of particles. And it took a very long amount of time to establish the existence of all these things and to understand the relations between them. So the big part is to understand what are the relations between these objects, how do they behave together, what are the interactions, how one transforms into the other, etc. And as for the relation, it took almost a century to understand what is going on with all this structure. Then you all heard about the Higgs field, or the Higgs particle. Maybe the thing that you heard most in the media is the Higgs boson. The Higgs boson is a manifestation of a field which pervades the universe, which is called the Higgs field. And the Higgs field, you can imagine the Higgs field as a kind of a medium in which all particles travel and live. And I mean all particles, also your particles, the particles which are made in your bodies, electrons and protons and neutrons. And the very fact that they live in this field gives them a property, which is the mass. The mass is a manifestation of the interaction of elementary particles with this medium which pervades the entire universe. And that is the Higgs field. This Higgs field has some excitations, which are called the Higgs particle. The Higgs particle is a kind of manifestation of the Higgs field. And then let's go to the composite particles. So the elementary particles, as we said, are the electrons and the muons and all that. And the composite particles are the particles that you know that you heard most about it, like the hydrogen. Hydrogen can be considered as a particle. Is a composite particle. It's made up of two things. One is the proton, and the other one is the electron. The electron is an elementary particle, and the proton, as we will see in a second, is a composite particle. The hydrogen atom has been described probably at school as a kind of gravitational system in which you have an electron which is orbiting around the proton with a trajectory. That is completely, as probably they already told you, that is completely false. There's nothing like a trajectory of an electron around a proton. Maybe if you really want to make a drawing, you can make something like this, in which the electron is basically somewhere around the proton, and you can only estimate which is the probability that that electron is living in some kind of unit volume around the proton. And then there are composite atoms which are more complicated than the hydrogen one, like, I don't know, this could be uranium atom in which you have a lot of electrons around and a complicated structure, which is the nucleus then. And the nucleus has its own way of behaving, its own laws, etc. And the constituents of the nucleus, protons and neutrons, are themselves composite particles. They are made up of quarks. In particular, remember these quarks that we had here, the U and the D. The U and the D are the basic ingredients of the proton and neutrons. And so the proton and neutrons do not exist as point-like particles. They are just clusters of more elementary things, which are quarks. And these quarks, the U and D, two U quarks and a D quark, live together in a kind of jelly thing, which is this proton. And the jelly stuff, which makes the glue of U and D quarks, are called G, like glue, like gluons, like this jelly thing that takes the proton together and the neutron together. So the nucleus of an atom is an extremely complicated thing. It's made up of a very complex object, which is the nucleon, which is a proton or a nucleus or a neutron. And then there is a structure around made up of electrons. Now let's go to the sizes of these things. We talked about the names, just the names of these things, the electron, the muon, the proton, etc. Now let's go about the size. There is an important constant in physics, which is the Planck Constant. And you probably heard about the Planck Constant at school, maybe. And then there is the velocity of light, which is c. And this number here is a number that particle physicists like very much. So if someone of you is ever going to do this kind of studies in the future, in some years from now, at some point, you will be exposed to this product of the Planck constants times the velocity of light. These are two fundamental constants of nature. The Planck constant is that constant that relates the frequency of a photon to the energy, as you know. And then the velocity of light is the velocity of light. It's 300,000 kilometers per second. And the product of these two is a number that everyone remembers by heart, which is given by 197 times MeV times Fermi. Fermi comes from the name of that physicist you heard about. And it's a unit of distance. Fermi is 10 to the minus 15 meters. This is another number to remember very well. And MeV means millions of electron volts. Millions is 10 to the 6. And the electron volt is a unit of energy. Electron volt is the energy which is acquired by one electron when this electron moves into a potential drop of 1 volt, right? After, if you put an electron in a potential drop of 1 volt, it will reach a kinetic energy, which is 1/2 the mass of the electron, times velocity squared. And that velocity squared times the mass gives an energy which is measured in electron volt, 1 electron volt. 1 million of electron volt is 10 to the 6th that unit, okay? This number is crucial. It's a number that is everywhere, more or less. So I will expose you to this number because we will gonna use it somewhere in our discussion. Now, atomic physics is related to a combination of the constant, the Planck constant, the velocity of light, and another number which is called the fine structure constant, which is 1 divided by 137. And this number here, as dimensions of a distance. Look at this. This is h, this is the mass of the electron, and this is c. Now, if you multiply, this is a pure number. Now, if you multiply the numerator and denominator by the c, the velocity of light, you will get at the numerator the hc, which is this beautiful thing that you have to remember. And on the denominator, you will get this pure number, 1 over 137, and then MEC squared. MEC squared is the famous Einstein relation. So MEC squared is an energy, as the dimensions of energy. So the mass of the electron times the velocity of light squared. And that energy here is the so-called rest energy of the electron. Okay, the mass of the electron in terms of energy. So it's 1/2 MeV. The numerator is Hc, is 197 MeV times Fermi. And Fermi, as I said, I repeat it, is 10 to the minus 15 meters. Okay, so it's a distance unit. So you will get, at the end of the day, that you have 137 times 197 MeV times Fermi divided by ½ MeV. And if you do this number here, you will get 0.5 10 to the minus 10 meters. So this is an example of a very important thing in physics. It's a very important guiding tool when you work with physics, which is dimensional analysis. You have fundamental constants, like the Planck constant, the velocity of light, and this alpha, which relates electromagnetic phenomena. These are fundamental constants of nature. And you have a problem to solve, and you try to understand which are the typical ingredients of this problem. We are talking about atomic physics. The atomic physics is related to this H constant, and it's also related to the mass of the electron. Imagine to the hydrogen atom. Look at the hydrogen atom. There is the electron and the proton. And you put together the fundamental constants in such a way to obtain a combination of them, which has the dimensions of, you want to talk about length? Length. So this is a combination of the constants which gives you a length. And that length that comes out from this combination of fundamental constants is a fundamental length of the problem that you are discussing. So the sides 0.5 10 to the minus 10 gives you an order of magnitude for the length involved in a problem in which you will be dealing with these fundamental constants. This is something that you do all the time. Think to the pendulum. When you do the pendulum at school, at least you did the pendulum sometimes, right? And there is the period of the pendulum, right? And you probably made a derivation for the period of the pendulum at some point. It's not necessary to make a derivation of the period of the pendulum if you want to know which is the typical size of the period of the pendulum for small oscillations, at least. You can make another kind of reasoning. You can say, what are the main ingredients of the pendulum? You know that the main ingredients of the pendulum are the length of the pendulum, and this is a length, is L. And then you know that another ingredient for the resolution of the pendulum problem is the acceleration, gravity acceleration, which is G. And then you can ask yourself, what other things you have? You know very well that even if you try with a little experiment, that the mass will not really enter this problem. If you change the mass of the pendulum, it doesn't change very much what you observe in terms of the period of oscillations, of small oscillations at least. And then you can try to put these two things together, which is the length and the gravity acceleration, to obtain something which has the units of a time. So length is length. The gravity acceleration is a length divided by seconds squared. So in order to make something which has dimensions of a time, you have to combine the length and g in such a way to obtain something which has dimensions of seconds. So you have to divide the length by g, and that gives you length divided by seconds squared, which makes seconds squared. So you just take the square root of this thing, and you obtain seconds in such a way that you can say, good, the period of the pendulum is the square root of L divided by G. And that should more or less be the period of the pendulum. And then if you made a derivation at school, someone told you, look, no, it's 2 pi, the square root of L divided by G. So there is a 2 pi missing in this reasoning. Actually, where is that 2 pi coming from? Imagine to take another thing, which is the conical pendulum, which is not the pendulum like the pendulum moving in a plane, but just another thing. You suspend a mass to a wire, and you make that rotate like in a cone, right? And then you project with a lamp the motion. You make the shadow of this object on a screen, and you look at the motion on the screen of the shadow. And the shadow on the screen will be doing the same oscillation of a pendulum in a plane, right? And these two things are related. And that 2 pi comes from the 2 pi of the circumference of the cone that is spanned by the conical pendulum. That is the place where the 2 pi comes from. But dimensional analysis is giving you the right thing. So here we know that the atoms are controlled by the Planck constant, and another thing which will come into is the velocity of light. And we put the things together, like when we solved the problem of the pendulum, in order to find the right sides of things. And this is the right sides for atoms, 10 to the minus 10 meters. What is the right sides for nuclei? 1 Fermi, 10 to the minus 15 meters. It's 5 orders of magnitude smaller than that. So nuclei are kind of very much smaller than an atom. And you know that an atom is made up of electrons somewhere around the nucleus. And then there is 5 orders of magnitude between the sizes of the two things. So an atom is basically something empty. There is a nucleus inside which is very small, 5 orders of magnitude smaller than the entire stuff, which is the atom. So everything, just since the electrons are like point-like things, between the two things, the electrons and the nucleus, there's just basically nothing. Now an exercise, you do the same thing here. You compute the typical length that is concerned when you talk about energies as large as 14 TeV, which is the LHC energy. And you were talking about accelerator in the previous hour. So you do the same exercise here. You put 14 TeV. TeV is the same as MeV, but is 6 orders of magnitude larger than that, okay? So this is about nuclei. Now you can ask another interesting question, which is the size of a single electron. So we said, this is the size of a nucleus. Then there is the size of the atom. The size of the atom is larger than the size of the nucleus. The nucleus is about something which is a number times Fermi. And now the question is, how large is a single electron, right? We said how large is a single proton and neutrons, more or less, which is the Fermi size. We said how large is a particle called atom. How large is an electron? You can do like this. Do you know about potential energy from high school? Remember potential energy from high school? You remember this form MGH, right? MGH, when you solve your physical problem, there is an MGH somewhere, which is potential energy. And you know where that potential energy comes from. There is a potential, gravity potential. This is the mass of something which is attracted by a larger mass, which is this M. And then there is the Newton constant in between, the universal gravity constant. And you have to divide by the distance between two things. Now imagine that you are on the surface of Earth, and the Earth has a surface, has a radius of r, capital R, and this capital R is about 6,378 kilometers. And you are at some height from the surface of R, which is x. And then you know that the potential energy is this product here, m times g times this, okay? And if you multiply the denominator and the numerator by r plus x, you will obtain g. And g carries a minus sign. And that minus sign is an exercise which I leave you on the next slide. It comes from the Gauss Theorem. You should know about it. Anyway, if you don't, you do this next slide to understand where that minus sign comes from. Anyway, this is the potential energy in the gravity case. And you know very well about this formula here. Now you do the same thing in electricity. If you do the same thing in electricity, you have to change the names of things. The mass is like a charge in the electrical case. So, you know, the Newton force and the Coulomb force have the same mathematical expression. It is charge times charge divided by distance squared. And the important physics is that distance squared in the denominator. And in the case of Newton, you have mass times mass divided by distance squared. And then there are two gossips, which are the constants in front. One is the Newton constant, and the other one is the Coulomb constant. I say that those are kind of gossips in the sense that if you redefine the notion of mass and you redefine the notion of charge, you can do in such a way that those two constants disappear. You kind of define, like there are units in electromagnetism which are called Gaussian units, according to which you have that the Coulomb force is just charge times charge divided by r squared, and the constant in front is like 1, okay? It's a different definition of charge. You can find a very unpractical, different definition of mass to do the same thing with the Newton law. So the constant can be kind of absorbed in the definition of electrical charges and the masses. So the very important thing is the dependency on the distance, which are here in this form. These are potential energies, not forces. You know that the force is obtained as a derivative of the potential energy, right? Now, you do the same in electricity. So you have a charge in place of a mass. You have this thing in place of G. This thing is the Coulomb constant. And then you have another charge in place of the mass and the distance divided by r. Which is the problem that you want to solve here? In this case, you have a mass which is attracted, a small mass which is attracted by a large mass. It's like U attracted by the Earth, and you know that this is reciprocal. In this case, you have an electron which is attracted by itself. So this is the place where the electron lives. You can imagine that the charge of the electron is scattered on that blue area. And then you imagine to compute the potential energy due to the interaction of the charge of the electron with the charge of the electron inside that blue area. It's a very interesting calculation, this one. Think about it. There is the potential energy due to the charge of the electron, and then you ask yourself, within a radius of r, what is the potential energy due to the interaction of the electron with itself? It's called self-energy. This is a very interesting calculation and gives a very interesting result. Look at this. This is E divided by R. This is the place where E is distributed. This is the analog of the Newton constant. Then you do the same job. You multiply times hc in the denominator and the numerator. And this number here is called alpha. You remember alpha is 1 divided by 137. And that is the same alpha which appears here. And then you get hc divided by r. And then you ask yourself, what is the classical radius of the electron? The radius of the electron, the so-called classical radius of the electron, is that radius that gives you an amount of self-energy, where self-energy is this thing here, which is as large as the rest energy of the electron itself. So it's alpha hc divided by r. R is the radius we are looking for, and we stop at mec squared. You see that? So this is an energy. The mass is related to an energy. And then you ask yourself, this self-energy can be bigger than the mass of the electron itself, right? This is an electron which is interacting with itself due to the Coulomb interaction. So it's producing an energy, this interaction. And you ask yourself, is this energy can be larger than the mass of the electron? It can't. It can't be larger than the mass of the electron. So what is the conditions for the two things to be at least the same? You put the radius here, a radius r, and you compute that r. And it comes out that it's 3 Fermis. And here you have a paradox. This is the first paradox in physics, which leads us to antimatter, and then we go to dark matter. The paradox is that if you do this very interesting and simple calculation, you find out that the radius of the electron is 3 Fermi. Why that is paradoxical? Go back to the nuclei. Look at the nuclei. The typical size is 1 Fermi. If you have a nucleus which has a mass a mass number like 27. The 27 cubic root is 3. So you will get, at the end of the day, 3 Fermi. So you are saying that a single electron is as large as a nucleus, which has 27 between protons and neutrons inside. You are saying that the electron is as big as a huge nucleus, which doesn't make sense. So what you discover with this simple computation here, which is basically a computation that you did at school, but just changing 2 things. Think about this fact of the product of the electric charge inside a space R, right? And so the potential energy, the self-potential energy of an electron. We discovered that you find that this is as big as a nucleus with 27A, which doesn't make any sense. So there must be something wrong in this reasoning. What is wrong in this reasoning? In this reasoning, the thing that is wrong is that when you go to very small distances as small as the distances we were talking about, 3 Fermis or so, you cannot use a theory in which you have only electrons around. You need a more advanced theory in which you don't have only electrons, but you have also a relative of the electron, which we did not mention actually in our first slide. We wrote E here. But E, in our mind, has a charge which is minus. Actually, E can have also a charge which is plus. And this is the positron. It's the antimatter of the electron. And what is fantastic is that if you write down this theory with the anti-charge of the electron, so it's a particle which is the same as the electron, but with opposite charge of the electron, you solve in one shot the problem of the self-energy here. So instead of having the trouble with the radius, which runs to be as large as 3 Fermis, if you have a theory which contains electrons and positrons, then it turns out that the radius will be much, much less than that. Actually, it could be a number compatible with 0. And that is because in this new theory, in which we have not only electrons, but also positrons, the rules of the games are different, and the potential at small distance doesn't not run as a 1 over r dependency like here. It's not 1 over r any longer when the distances get smaller and smaller and smaller, but it runs with a different law, which is logarithm of r, instead of 1 over r. And the logarithm of r is much slower when it goes to r to 0. And now, exercise number 2, go back to this thing and just try to understand why, since the logarithm is different from 1 over r, you get a much smaller radius of the electron in this case, with respect to the case with 1 over r dependency. So you see, this is a departure from the theory. We discovered that that potential energy changes from 1 over r when you go to low distances, to small distances. And this departure could be a departure that is somewhere also in gravity, for example. And probably it could happen that gravity changes when you go to very low distances. It's not 1 over r. And it could be that gravity changes also when you go to very large distances, as we will discuss in a second, talking about dark matter. Exercises, again, you have to compute the numerical value of the electron's classical radius, which is something which is already in this slide, but you have to do it. And also, you have to find out this following thing. Can the logarithm of r just be a right mathematical formula? Because r has a dimension of a distance, and the logarithm of a distance doesn't make really any sense. This is because if you take the logarithm of a distance and you say logarithm of r is equal to y, then you take the exponential of the left side and right side, and you get r equals to e to the y, right? And then you ask yourself, can it be that it has a dimension, the logarithm? So the argument of the logarithm, can it be that it's a dimensional quantity? Or it has to be a quantity which has no dimensions, right? If you take the exponential of x, can x be 1 meter? What does it mean? If you take 5 to the x, can be x meters or seconds or whatever. Can it be? No. And why can it be? Why can't? Because 5 to the something means 5 multiplied by 5 a number of times which is written in the exponent. 5 to the second power means 5 times 5. Now, if the number in the exponent is 1 meter, what does it mean, 5 to 1 meter? You have to multiply 5 times itself 1 meter times? So it can't work. Now, the logarithm is the inverse of the exponential, and there must be something there. So the argument of the logarithm must be adimensional, dimensionless as well. And try to understand if the right dimensions of the argument should be of this kind or of this kind or whatever. You have all the things to do it. Now we go to the opposite side of the problem. So we discovered that there is dark matter, there is antimatter, so particles which have opposite charges. What I didn't say here is that this story repeats for all the particles which were in the first slide. So every particle has an antiparticle. Sometimes the antiparticle coincides with the particle, sometimes. There is nothing strange about antimatter. There is no Star Trek physics about antimatter. Antimatter is just like matter. It is just specular matter in terms of charges or in terms of other quantum numbers that we cannot describe today. But there is something which is opposite. In this case, charge. In other case, there are something else. But this is it. Now let's go to the second topic, which is the dark topic. This is matter. You can see electrons. You can see positrons. You can see them. You can produce positrons, which is antimatter, in labs. And this is actually done every day. You can see protons. You can see antiprotons. You can see quarks. Quarks, the building blocks of protons, exist. You see them somehow. All these things are seen in an indirect way in complicated experiments, but are seen, right? Now we will be talking about what is not seen and what we think that is there, which is antimatter. Let's again make use of the Gauss Theorem. Now imagine that you have an amount of mass here, right? And this amount of mass is concentrated in a sphere which has a radius of small r. And then this is capital R is another sphere which includes the first one. In the red one, there is mass concentrated, and so there is a bulk of mass in that. And then there is a big sphere surrounding it. And then you ask yourself, OK, what is the gravity acceleration when I am somewhere? No, sorry, let's about the problem. So this capital R is just a bulk of mass. So everything is full of mass inside capital R. And then I look, and I take a sphere which is smaller than the radius of R, and I ask myself, what is the gravity acceleration on that red sphere? So the black sphere is the Earth, and the red sphere is some surface inside the Earth. Imagine to be sitting on that red sphere. Imagine that you have an elevator that brings you back to the center of the Earth, right? And that elevator that brings you to the center of the Earth is allowing you to be sitting somewhere on this sphere when the radius small r goes down to 0, right, to the center of the Earth. What is the gravity there? We already used this formula. It's g times m divided by r squared, where this is small r. And then what is m? M is the mass which is contained in the red sphere. It's not the mass of the Earth. It's the mass in the red sphere. And that is the sense of the Gauss theorem and the fact that when you are sitting on the red sphere, you don't feel the attraction of the mass which is outside the shell you are sitting onto, right? You don't feel the attraction of all this thing. You just feel the attraction of the mass inside the red sphere. This is a very important result in physics. So when you are sitting on the red sphere, you just feel to be attracted by the red sphere. If you have a mass which is surrounding you, you don't feel that attraction. Very important thing. This is a result which holds in 3 dimensions. It doesn't hold in 2, but we are in 3 dimensions, and so we will be talking about this result. It doesn't hold in different than 2 dimensions. Then we can talk about this. Anyway, what is the mass m? Is the mass in the red sphere. And what is the mass in the red sphere? Is the density of mass in the red sphere, careful with that, is the density of the mass in the red sphere multiplied by the volume of the mass in the red sphere. Density times volume is a mass. And that's it. So you have r cubic in the numerator and r squared in the denominator. And this is the definition of G, right? And what do you get? You get something which scales like R. Another point, now, if you have now, imagine another situation in which you are not sitting on the red sphere, but imagine that you are a star, and you are a star, and you are going around this center on some trajectory on the red sphere, for example. So you feel the attraction of this mass inside the red sphere, and you are doing circular motion around that region. If you do circular motion around that region, you do a circular motion and you feel the G, which is computed here. On the other hand, circular motion gives you that G is the acceleration in circular motion is v squared divided by r. This is the acceleration in circular motion. Do you know that? Hopefully you do. So if you put the two things together, you get that v goes like r. So v goes like r. Interesting fact. Now let's go to the next slide. You go with a r which is larger than capital R. You are not inside this distribution of mass. You are outside this distribution of mass. Why I'm saying so? This mass could be as dense as the mass of the Earth, but could be also a mass which is not as dense as the mass of the Earth. It could be like a gas. So the big sphere R could be a sphere full of gas with a distributed mass. So there are empty spaces inside. And you can be a star moving in this gas. And you can be a star moving in this gas at a distance from the center of the gas, which is more or less r. And your velocity will change like r. You will be faster if you go with a larger small r. You will be slower if you go with a smaller small r, moving in this gas. Of course, you cannot orbit inside the Earth because the Earth is very dense, so you don't have space for doing that. But you can do that in a gas. So there is not such an important difference between the two things. It's just a matter of density. Now you go with a distance which is larger than r. So instead of being inside this cloud of gas, for example, you are here, somewhere here. In that case, the G is Gm divided by r squared. And m is the mass contained in the entire sphere. Okay? It's not the mass contained in the red part of the sphere. It's not 4 pi divided by 3 r cubic times density. It's the mass in the entire sphere. If you solve the same problem, you will get that the velocity goes like 1 divided by the square root of r. So if you are inside the gas, the velocity grows with r linearly. If you are outside that region, the velocity drops down like 1 over the square root of r. And that's what happens, and that is what you suppose that happens in the Milky Way, which is the galaxy we are in. The galaxy we are in looks like a bulk of stars, pretty dense. And this bulk of stars, which is pretty dense, is concentrated to the center of the galaxy. Then as you go outside of the center of the galaxy, like we are in a very peripheric way of the galaxy, very peripheric place of the galaxy. Well, if you go outside, you get less and less dense. So you can try to simplify the problem, as usually is done in physics. The first calculation you do is the most simple calculation you can. You can simplify the problem and say, okay, the most of the mass in the galaxy is concentrated to the center, which is this orange ball. And actually, if you move out from this ball, you will not have too much mass around. The bulk is here. So it's the same problem as the problem we solved right above. So if we are inside the bulk, the situation is like this. If you are outside the bulk, the situation is like this. So we can look at the velocity with which stars go around the center of the galaxy, and we can try to understand if this plot that we made here makes any sense. If we look at stars going around the center of the galaxies, they should have a velocity which goes like the distance from the center, which goes like this. If you look at stars which are far away from the center of the galaxy, they should have a velocity which changes with distance with a law which is like this. So this is a star, and the star we have there is the sun. And the sun is a star which goes around. It moves now to the direction of the Cygnus, and that moves with a velocity, and that velocity should be proportional to the distance from the center of the galaxy. And so, in a way, we can estimate that velocity because of that. You know what? It turns out that the sun goes at a velocity of about 260 kilometers per second, which is, sorry, 232 kilometers per second, which is about, if I remember well, about 50 or 60 kilometers per second faster than what it should be, according to this law. Now, you can ask yourself, well, you made a mistake somewhere. Probably this calculation is too simple. Probably there is something which is missing in these formulas. Probably that discrepancy is not so disturbing for who knows. Well, this problem has been there for 50 years. And people are tried to understand where is the mistake, if there is a mistake, if there is something wrong. And people have tried to do different observations, trying to understand if this behavior is there, not only for the stars in our galaxies, but also for more distant objects. And the behavior is there. Indeed, what is observed is different from what is computed in this way. This is the behavior inside the ball, and that is the behavior outside. This is what is observed. This is what it should be. Somehow there is a discrepancy between the two things, and the discrepancy is always in the same direction. Everything moves faster than what is expected to be the real amount of. So what are the ingredients in these calculations beyond the behavior 1 over square root of r? The mass of the stars that you can estimate at the center of the galaxy, a number of things. But qualitatively, it doesn't go down like 1 over square root of r. It goes flat. It goes flat. This is astonishing. So it's 60 kilometers per hour, per second, the difference. So it's like the gravitational pull is way larger than what can be estimated as due to stars. Now, it comes, the problem comes to the mind. One says, the antimatter has been discovered. Well, it's not exactly the story of antimatter, but antimatter is there, and you realize that antimatter is there, and you see that the antimatter is necessary when you understand that the behavior of the Coulomb potential at very small distances is just wrong if you use the classical formulas. It's not 1 over r. It's the logarithm of r. So there must be something wrong in the potential of electricity at very small distances. So the question could be, is there anything wrong about the potential of gravity at large distances? We are at very large distances from the center of the galaxy. The sun is very far from the center of the galaxy. We know that the Newton law works perfectly well in the solar system. We know that the Newton law was fantastically well with the moon and the planets, etc. But do we know everything about the Newton law when the distances are as large as the radius of a galaxy? Again, this is the same as the Coulomb reasoning. Do we really know what happens to the Coulomb potential when we go to distances which are as small as the Fermi size? In that case, we discovered antimatter. In this case, we could discover something else. So this is a line of reasoning which has been tried. And the line of reasoning is, take the Newton law and says that it's wrong at large distances. This is called MOND. MOND theory have this in their minds. What are the distances we are talking about? So in the few slides at the beginning, we were talking about distances which are as small as Fermi and 10 to the minus 10 meters and all that. Now the distances are measured in parsec. Parsec is a ridiculously large distance. The parsec is compatible with 3.26 light years. So you see that you are going to the opposite sides, from the very small to the super large. And the parsec is basically defined in this way. This is the distance. This is the size of an object with 1.5 10 to the 11 meters, 1 astronomic unit. And this is the angle. You see this, and this angle, this is the observation point. This is the angle with which you observe this large object. And this angle is as large as 1 arc second. So you see an object which is 10 to the 11 meters under 1 arc second. How far are you from that? Huh? So these are the kind of science. So look at this plot. This is 10 kiloparsec, 30 kiloparsec, and this thing works even at that distances. So if you look at the motion of stars on immense distances as large as 10 kiloparsec and 30 kiloparsec, you see that the behavior is again that kind of. It saturates at this velocity here, like if there is something special about that. So what is the hypothesis that you can do about it? What would you imagine? What we see is that the gravitational pull is larger than it is supposed to be. Why the gravitational pull should be larger than it is supposed to be? The most obvious reason why a gravitational pull should be larger than what it's supposed to be is that there is more mass than what we think it is there. The less obvious reason is that there is something wrong in the law. As we said before, there could be something wrong in that 1 over r behavior. There could be something wrong in the amount of mass we estimate. So the most conservative thing is to imagine that there is something wrong in the amount of mass we estimate, and that the Newton law holds also at very large distances. So this is the prejudice. This is the attitude which is used in this field. It's not like the reasoning which brought us to antimatter. It's another kind of reasoning. Say, let's be conservative about the Newton law, and let's imagine that we did something wrong about the amount of mass we estimated to be around. And, OK, I should stop this, sorry. So, this is the bulk of stars. This is the galaxy. And this is something else that we didn't include in our reasoning. This is dark matter. Why we call it dark matter? Because you don't see it. You see the stars are bright. And everything which is not bright and you don't see, you call it dark. In the center of the galaxy, there is a bulk of stars that you can see. In the periphery of the galaxy, there is a lot of stars that you can see. And then there should be some halo, which is kind of distributed spherically around this bulk, which you don't see. Is there any exotic about what you don't see? Again, this is the same question as antimatter. Is there any exotic about antimatter? It could be that there is nothing exotic about dark matter. The Earth is dark matter, more or less, because the Earth is not emitting light. Can you see the Earth from outside? Yes, because of the reflection of the light from the sun. But imagine to have a rock somewhere far from any star. You see the rock? Imagine that you look at the universe. What do you see? You see the stars, because they emit their own light. But you see dust, the rock, and rocks and things like that. You should be shading light on them to see them. But you don't have that tool, right? So it could be that dark matter is just dust and planets. And so that there is a lot of dust and planets around. We don't see them. And that is dark, period. Doesn't work. People have tried this very hardly. It doesn't work. It doesn't work for many reasons. It doesn't work because the amount of mass which is computed to be in stars is more or less what it was supposed to be. It doesn't work also for other reasons which I will show you in a second. It just doesn't work. So it can't be dust and planets. Imagine about dust. Imagine that we are in an immense amount of very tiny dust, which is massive, which provides you mass, especially on these distances. So it is changing the gravitational pull, but you just don't see it. Now, you look outside in the space, you should see that astrophysical objects which are far away in the space, you should see them more opaque because of this dust in between, right? But that doesn't happen. So it can be dust. The density of this dark matter locally is about 10 to the minus 25 grams divided by centimeter cubic. And then you can think, okay, that is not a big deal because 10 to the minus 25 grams is a very small number. Look at the mass of the Earth. The mass of the Earth is 5 grams per centimeter cubic. So we are immensely much. Yes, but the Earth is a localized object. The Earth is here. That's it. This 10 to the minus 25 grams divided per centimeter cubic is distributed on an immense region in a more or less uniform way. So there is much more than dark matter than matter. Matter is localized in clusters, which is the Earth, Mercury, the Sun, etc. And dark matter is everywhere, with a much less density, but it's scattered everywhere. So there is a lot of dark matter. So the identikit, that interacts gravitationally, otherwise we wouldn't have realized about those curves. That doesn't emit UV, infrared, X-rays, radio, it doesn't emit anything. It's just dark. It probably pervades the entire universe, not only our galaxy. And that is maybe in a pretty much uniform way. It should be cold. This is another story. It's not planets or rocks or dust. And distant object would look much more opaque if it were for dust, for example. So it must be something like that. Then there is another beautiful fact, which is called gravitational lensing. This is you. You are observing far out in the universe. This is for example, it can be a cluster of galaxies. A cluster of galaxies means a cluster of galaxies. Which is there. And then in between you and the cluster of galaxies, there is a lot of stuff because you are looking to a very far away cluster of galaxies. So there is a lot of stuff between you and this. And this stuff is matter, stars, and a little bit of planets, plus dark matter, which is something we don't know, actually. Then there is this important fact, which is called gravitational lensing. The matter and dark matter between you and the distance object, it is able to change the geometrical laws of the space. Matter, in general, has an influence on the geometrical law of the space. You can imagine that matter can change the rules around it in such a way that the shortest path from O to your eye is this way instead of being straight. And that is because the geometry changes. So the shortest path connecting 2 points is not the segment, but it's a curved path. Think to the Earth. Think if you go with the plane from Rome to Los Angeles, what do you do? If you go from Paris to San Francisco, which is the typical route you do, you go straight? No. You go a little bit northern, you go to Greenland, and then you go to Canada, and then you go down. If you look at the path, it's not exactly the same path you would have drawn on a map. Think to the map, you have the map. This is San Francisco, this is Paris. You take the pencil and you go straight like that. This is not what the aircraft is doing. Why is it not doing that? For 2 reasons. 1, saving time. two, saving fuel, and the two things are connected, but they care more about the fuel. And so they want to go to the shortest path. And the shortest path on a sphere is not the same as putting the sphere on a plane and draw a segment between the two. So it's like that matter changes the geometry of the tree space. Now, from the b-dimensional flat map to the sphere, you imagine exactly what I'm talking about. Now you have to imagine the same thing with a three-dimensional space. So you can't imagine it. You have to imagine that the flat map is the three-dimensional space, and then you wrap the flat map of the three-dimensional space on a sphere. But this sphere is in one dimension more. It's a three-dimensional sphere. You can't imagine, but it's the same thing. So the matter is known from general relativity to change the rules in this way. So this is the path from Paris to San Francisco, and this is curved. Okay? What is your extrapolation? Well, you see things, and what you see, when you see the light coming from here, look at the path. This is close to your eye. The path close to your eye is like this. This is the long path. This is Paris, San Francisco, and this is just close to San Francisco. This is very small. You extrapolate the position of the object to be here. Because if you look to a source of light, and the light comes from that point, you think that that is the origin of light. So you extrapolate straight. If you look at something, you see a spot of light, and you put the finger, you say, it's there. It's not there. It's somewhere there. But you say that it's there. This is the extrapolation you do. This is close to you. You say, it's there. This is another bunch of rays that comes from there. And you say, it's there. So you know what? You look at copies of the same thing, which are dislocated in places here and here on the entire circumference. And they are the same thing. A kind of image copies. This is called lensing. It's gravitational lensing. It's due to the fact that the tree space is wrapped on a supersphere, which is three-dimensional. And this is very well known. It's computed in general relativity, which is the gravity theory of Einstein. It's computed in very precise ways. And general relativity is no abstraction at all. The GPS mobile phones that you have contain corrections of general relativity to higher orders. Otherwise, they couldn't work how they do. It's unbelievable how much is known that theory and how much is hardwired even in your technology, in your pocket technology. And this is an image of what we were talking before. This is the bullet cluster. And, well, with all this light, it's not clear that you see very well. We should be switching off the lights here. But there's no one doing it. So we're going to, do you see something? OK, so you see something blue here. And there is something blue here, more or less. Something red, something red. So the bullet cluster, it's a kind of collisions. It's a kind of collision of two clusters of galaxies. Actually, there is a subcluster moving out from a cluster. OK, grazie. Forse. OK, perfetto, grazie. So you see, red is the, so imagine that you have a cluster of galaxies, which is packed with stars and gas. And there is another cluster of galaxies. Cluster of galaxies is an immense thing. And another cluster of galaxies, which is, again, stars and gas. And imagine a collision between these two. One goes through the other. Now, the cross-sections of stars is small, in the sense that the probability that two stars will be colliding is just. So when the two clusters of galaxies go one through the other, The stars more or less go straight. One follows the first, and the other one follows the second. So they go through the interaction point. As for the gas, which is more distributed, the gas is more prone to interact in the interaction region. And there will be a lot of interaction actually there. And you will see the interaction of the gas in terms of X-ray emissions. So you will see that the two gases are squashing one with the other, and you will see the effects of those in terms of X-rays. And this is more or less the X-rays that come from this region here and here. So there is a part in between, which is pretty much reddish. And then there is these blue things. These blue things is dark matter. Now I will tell you how. It's not that you see the dark matter, because dark matter is not emitting anything. It's not emitting UV, it's not emitting X, it's not emitting anything. So there is nothing blue there. That is the reconstruction of the gravitational lensing I was talking to you before. So imagine that this cluster of galaxies is surrounded by a bulk of dark matter. So there are stars, gas, dark matter. And the other one is stars, gas, dark matter. They go one through the other. The stars go straight. The gas makes a lot of mess, interacts, and emits X-rays. And what is dark matter doing? Well, dark matter is supposed to be very much weakly interacting with the rest of the world. Otherwise, it would be emitting UV or infrared of X, etc. The very fact that it's so much sterile, is so much not interacting with the rest of the world, is telling you that dark matter should go straight, more or less like the stars, even more than the stars. Like dark matter should be absolutely not disturbed by the interaction of two clusters of galaxies. Should go like that, no problem. They don't touch. And indeed, what gravitational lensing is telling you is that you have a big amount of dark matter here and a big amount of dark matter here. And then there is an interaction region which is red, which is what you see. So this is a kind of gravitational evidence, a second gravitational evidence of dark matter. The first one is the rotation curves. The fact that the velocity is not what you expect to be. The second one comes from gravitational lensing, which is this phenomenon I was telling before. To tell the truth, the first one is absolutely solid. Everyone trusts the first one. Everyone knows about the first one, and the first one is something that you cannot dispute. This one, it was supposed to be one of the best things about dark matter known, but it's not really like that. There are people who think that there is something wrong in this observation. So this is weaker, in a way, with respect to the rotation curves I was discussing before. Anyway, this is great. It's a very interesting phenomenon. I think that I have to stop anyway, because I'm just 5 minutes there. And so I prepared twice as much as I was able to speak about today. So you will find this stuff. The remaining part is, wow, it's very long. So, well, this is the conclusion. The conclusion is dark in the sense that the end of this story is not known. This is a beautiful problem that probably will be in your hands when you will, for sure will be in your hands. I'm not pretty sure that it will be solved until some of you do physics, if any. And it won't be solved in 5 years. It has not been solved in 50, so it's unlikely to be solved in very short times. Anyway, this is a very interesting problem, and this is one of those interesting problems which you know this, more or less.